About this very interesting connection between bootstrap percolation and statistical physics.
Thank you so much for the invitation. Okay, so this is the third and maybe last talk about connection between bootstrap percolation and this kinetically constrained model that Christina spoke about on Monday. So this is an ongoing project with Christina and Rob Morris in IMPA in the framework of a ERC grant that Christina just started in Paris. Okay, so I mean, since I'm the third one, I had two options. Either, assume from start that you remember very well the talk by Christina and Paul Smith, or to repeat. And I decided to follow the easy second route. So I will recall you, briefly in the first slides the content of the what bootstrap percolation is and kinetically constrained model, and then proceed to some conjecture and result. Okay, so bootstrap rule is a cellular automaton which works like that. So you have a finite collection of subset of, say, Z2. We will always work on Z2 today. And each vertex can be either infected or not. And the rule is the following, that, say, the origin, if it is not already infected, in the next round of the dynamics of the bootstrap percolation will get infected if at least one of the set x1 up to xm is infected. Okay, then also the root will be added to the infected vertices, and then exactly the same rule applies for any other vertices, provided that you translate all the set, as if the vertex is the origin. And then you call A sub t the set of infected vertices at time t. And so formally this U bootstrap process is, so you add to A sub t, you add all the vertices that were not infected and that could be infected in the next round, and then you create A sub t plus 1, and you proceed infinitely many times. And the closure of the initial set of infected vertices, A, is called this with square bracket. And so this is the union overall possible time of the infected vertices. Okay. So here are some examples of the most common processes. So the R neighbor process. So you, in order to be infected, you ask that at least R of your 4 neighbors are infected. Then there is this, maybe the proper name would be south or west process, but actually is known in the literature in physics as the east model for historical reason. Okay, and so you need at least one of your south or west neighbor to be infected in order to become infected. And then, for example, there is the northeast process, which requires the north and the east neighbors infected in order to become infected. Okay, so these are just examples, of course, but so the main question is, so take a big torus, say lambda n, and suppose that you start by tossing a coin for each vertex in order to decide whether it is infected or not. So this is, so the initial set is p random, so the probability to be infected if p, which is assumed to be very small. Okay, and then you ask, so you define the critical probabilities as the infimum of the values of p, such that the probability that eventually you will infect all the torus is at least, say, 1/2. 1/2 is just some convention threshold. And so the main problem is to study the behavior of the critical probabilities as n tend to as the side of the torus tend to infinity. Okay, so a key contribution by Bella, Paul Smith, and Atzel was to identify that the behavior, the scaling of this critical probability is dictated by the action of the bootstrap properties on discrete half plane. Okay, so they introduce this notion of a stable direction. So stable direction maybe is better illustrated by this picture. So if you take a direction u, you take the hyperplane to the left, orthogonal to u to the left, and you suppose that all this is the half plane. Sorry, not the hyperplane. The half plane is all infected. Then u is stable if this half plane of infected vertices is not able to propagate inside. Okay, so this is forbidden. So then you say that this is stable, and then they came up with a general classification which says the following, that so the bootstrap process is supercritical if there exists an open semicircle with no stable direction. It is critical if every semicircle has non-empty intersection with the, so contains some stable direction, and there is one with only finitely many stable direction, and subcritical otherwise. Okay, so here are some examples, just to make a connection with the example. For example, if in the one neighbor process, so one neighbor again means that you require that at least one of your neighbor is infected, just one. Okay, so there are no stable direction. So green typically means non-stable. Now the east process, or the south and or west process, this is supercritical, and so the stable direction are in this quarter of a circle, the red one. If you require at least two neighbors infected, then you get this far stable direction, and therefore it is critical. And the northeast process is subcritical because it has this 3/4 of a circle that is stable. Okay. And then the same people, and with the addition of another one for this case here, they proved this beautiful theorem, so that the scaling of the, for as n goes to infinity, of the critical probability obeys this behavior according to whether the bootstrap percolation is supercritical, critical, or subcritical. And then today we will be only concerned with the either supercritical and critical case. Okay. Okay. So for what I want to say about kinetically constrained model, is more convenient to reformulate everything not in terms of the critical probability, but more on critical scale. Okay. So imagine that you fix a very small number p, okay, and call L sub c the critical state, such that the critical probability is equal to p. Okay. Then another way to formulate the first two lines of this theorem is that if the system is supercritical, then this critical length scale behaves like the inverse of a polynomial of p when p goes to 0. And if instead it is critical, then it behaves like an exponential of 1 over p to a power. So I didn't mention the extra result that they proved, namely that, so they introduced, and Paul explained in his talk the other day, this notion of difficulty alpha for a system, and then they identify exactly the correct power in this log here, which translates for length scale in an exponential divergence of the critical length with in the inverse of p to a specific power. Okay. Okay. So this is, so far as we explained the bootstrap model. So now let me remind you what kinetically constrained model are. So I would say that so far the mathematical development of kinetically constrained model mostly concentrated around studying some specific model, for example, the East model, in great detail, and so these are processes that are very rich with some surprising behavior also. While here in this talk, I will try to see whether it is possible to have some kind of universality result of the kind that that Bella and collaborator obtained for Bootstrap percolation, also for kinetically constrained models. So it's a little twist in perspective. Okay, so back to the model. So first of all, they are interacting particle system, namely on the lattice at each vertex you have associated a Boolean variable 0, 1, and this variable they change in a way that they form a Markov process. Oops, sorry. Okay, so in particular they are reversible. So they are reversible Markov process or reversible Markov chain, whether you are on the infinite lattice on a big torus. So conventionally we associate the value 1 to infected and 0 to not infected. And so a first key feature of this KCM is that the reversible measure is completely trivial. Just describe IID variable, so in which no probability of being 1 is P. So they do not feature complex like Gibbs measure, like in other statistical physics, spin model, easy model, Potts model, or related. And they are very closely related to Bootstrap process, but they are not monotone. So in the Bootstrap process, the set of infected vertices can only increase in time or not decrease at least, while here the set of infected vertices can increase but also decrease. Okay, so that adds many new features. So the KCM process can be defined as follows. So you fix a Bootstrap rule exactly as before, okay, and then the updating rule is the following. So in discrete time, so you pick a vertex and then you check whether the vertex could be infected by the Bootstrap process, is infectable, okay? And then if it is infectable, then you toss a coin, a P coin, and then you decide that it is infected with probability P or non-infected with probability 1 minus P. So even if the vertex was already infected and it is infectable again, then it could heal, okay, or remain infected, okay? So it can go back and forth. So in continuous time, which is the convenient way to describe the process, then each vertex with rate 1, according to some Poisson clock, does exactly that.
The next state is independent of the present state.
The next state is independent of the present state, provided that the vertex could be updated, namely if it could be infected by the Bootstrap map in the underlying Bootstrap process. Okay. So, for example, here in the two-neighbor process, for example, this vertex is allowed to move because there's two infected neighbors around. These two the same, while this one not, because there's only one infected vertex around. Okay, this just two. So the main obstacle for mathematical analysis is that these processes are not monotone. So if you inject more infected vertices in the system, the outcome is unpredictable, actually. So there are no FKG inequality or say censoring available. If you try to do worst case analysis, for example, with respect to the initial condition, that's usually too rough, okay? Because if you put everything that is not infected, nothing will move, okay? And also, inequalities that govern the relaxation to equilibrium of this model, like Poincaré entropy inequality or the log Sobolev inequality, they behave differently from the corresponding inequality in the context of more like standard spin system in StatMech. Okay? Okay, so what is the main object that we will focus on? This, so we can define the infection time, say, of the origin. So it's the first time that the origin is infected during the evolution. Then after that, maybe the origin will heal, then will be infected again, and so on and so forth. Okay, but we look just at the first time. Okay, and the main problem is what is the growth of the infection time when p goes to 0 in a supercritical or critical system, and say either in probability or in mean with some concentration or not, that will depend. Okay. Now there are general bounds on this infection time, which is the following. First of all, the infection time is bigger than some constant, some numerical constant epsilon, time the critical length scale of the corresponding bootstrap process. So this is the first connection between the two worlds. Okay. However, we will see that this inequality can be sharp in some model, but not sharp in other model, and we will have to sort of refine the classification of that was proposed for the bootstrap model.
Isn't the time a random variable?
Yeah. So okay, so here I'm a little bit sloppy, namely, say here is the mean, so it's okay, but here let's say with very high probability, or okay. So the second, the upper bound is instead, and actually we have stronger bound that proves some concentration, is that the average, if you start from the equilibrium distribution, so the reversible product IID measure on the lattice, then the average of the infection time is order of the relaxation time of the chain or of the process, and I will explain what this is in the next slide, divided by p. Okay, so these are essentially the two general bounds that we have at our disposal. Now the relaxation time is the following. Okay, so there is a little digression in, say, Markov chain or Markov processes. So you have the quadratic form of the generator of the chain, so it's the Dirichlet form of the process. And for KCM process, this takes the following form. You sum over all vertices, and you take the average of the local variance of a function. Local means with respect to the variable, to the Boolean variable at x only, having frozen all the rest. However, this is multiplied by the indicator c sub x, that actually that vertex is infectable by the bootstrap map, which means that this vertex can actually move under the KCM dynamical rule. Okay, and then so given this Dirichlet form, then the relaxation time is just the best constant in the Poincare inequality. That says, so the Poincare inequality is the variance less than constant times the Dirichlet form for any function f, if you are on the infinite lattice for any, say, local function f. Okay, and this is what we call a constrained Poincare inequality, because constrained because in front of this local variance there are this indicator function that can be either 1 or 0. Okay. So, for example, in say easy model, you have the similar expression, but then the constant in front are strictly positive uniformly in the configuration, while here they can be 0, and this opens a new world of possibility. Okay, so, and actually the relaxation time, sorry, maybe the last information is that if you have a reversible Markov chain with a relaxation time, say t, then the decay to the reversible measure in the L2 sense is exponential with a time constant which is exactly the relaxation time. Okay, so which are the general tools to bound the relaxation time? We saw that the relaxation time is roughly proportional to the average of the infection time, so it's interesting to have good bounds on the relaxation time. Well, lower bound you can use just the variational characterization. So just, the tool is figure out a good test function, f, and then compute the variance and divide it by the Dirichlet form of that function. That will give you a lower bound on the relaxation time. So apparently this is the easy route because you just pick some function and you plug into the variational characterization. However, in order to get really meaningful bound, you need to sort of understand a great deal of the process in order to find a good test function. So the upper bound is usually much harder because you have to prove a constraint Poincare inequality, namely variance less than some constant, the Dirichlet form, and then the relaxation time will be at most that constant. Okay, so these are basically the two routes that one has in order to control this relaxation time. Now, I said that the KCM are not monotone in the sense that if I inject more infected vertices, it's not at all clear whether we will get for all later time more infected vertices or not, okay? Because infected vertices, they can make more vertices to heal and therefore decrease the number of infected vertices. However, the relaxation time being expressed in terms of Dirichlet form and variance has some monotonicity property. In particular, if I have a family of rules of Bootstrap rule that is contained, so U, which is contained in another family U prime, then actually the stable direction of U is richer than the stable direction of U prime, and the relaxation time for U is bigger or equal than the relaxation time for U prime. So sometimes could be useful to compare two different KCM and say the relaxation time of this KCM is bigger at least of the relaxation time of another one, okay? It is quite natural to ask whether this monotonicity is true, holds, forgetting the first part, namely this one, and just asking whether, just asking that the some inclusion between the stable direction of two models, okay? And actually the answer, just by looking at specific example, is false. So it's not true that that if a model has more stable direction, then automatically the relaxation time of the associated KCM is bigger than the relaxation time of the other model. Okay, so this is important. So let me describe the scaling as p goes to 0 of the relaxation of the infection time for some specific model. Okay, so for the one neighbor process, this was done by Cancrini, myself, Roberto, and Cristina in 2008, and then later by Pillai and Aaron Smith in 2015. And so the scaling is inverse of a polynomial, and actually we also know now the power. Then the south or west process, namely the east process. Okay, this was well, originally this was computed by David Aldous and Percy Diaconis. Then later by the same people here, and then David and Percy computed the relaxation time for the same process in one dimension. Then these people also computed in one dimension, and then in two dimension, actually in any other dimension. Paul Klebon, Alessandro Fagionata, and myself, we computed precisely and as this new form that we didn't encounter before in the Bootstrap process. And actually, we were able to compute exactly the constant multiplying this log. Okay. Notice that for the south or west process or east process, this scaling is very different from the scaling of the critical length, which is still is a subcritical process. So this is still a inverse of a polynomial. Okay. While here we get something that is much bigger. Okay. So this is the first main difference between the two processes. Okay, and then for the two neighbor process, which is a critical system for which is actually known that the critical scale behaves like exponential with a precise constant over p. Then with Cancrini, Roberta, and Cristina, we only had in 08 a bound which was the critical scale to a large power, 1 over p cube, okay? And I will discuss today possible route to actually get essentially power 1 apart some polylog, okay? So let me describe some intuition behind this strange growth of the infection time for the east process, south or west process, okay? So the system features what physicists call logarithmic energy barriers, and I will try to explain that. And the best way to see this is to discuss the situation in one dimension. So in one dimension, the model is like that. So a vertex can be infected if the left neighbor is infected. Okay? Otherwise, the vertex cannot move. Okay? And let's say that, sorry, I'm making a mess with this. Oops, I apologize. Okay. So, and let's say that the energy is the number of infected vertices. Remember that each infected vertex has a cost p in the equilibrium distribution. Okay? So, let's say that we want to infect the origin, and let's say that if we look to the left, then we find the first infected vertices at distance n. Okay? So in order to infect the vertex, this infected guy here has to bring some infection up to here, and then we can infect also the origin. So the main question is, how does the path from this vertex to this one grows, putting some infection? Well, this is actually brings up a combinatorial question that was solved by Chung, Daconis, and Graham in 2001. And they proved the following, that in order to bring infection to this vertex here, you have to create at least log base 2n vertices that are infected. Okay? So since every vertex has to pay, is a cost in energy, okay? So you see that you have to increase the energy by an amount that is at least logarithmic in the distance, and this is what physicists call logarithmic energy barriers, logarithmic in the distance, okay? Actually, they also refine the result, saying that how many configuration can you visit during that, and then they compute exactly this number, okay, very precisely. So given that, we can sort of conclude, namely compute the probability that the infection time is less than t. Well, if you do a union bound over t, so you have some proportion of t here, and then you have to compute the probability that you find between 0 and minus n log 2 base log 2 of n infected vertices, and okay, you just do some very simple estimate. Now you choose n, which is 1 over a small power of p. Now 1 over p is the equilibrium distance between infected vertices in equilibrium, okay? And then you get immediately this expression, okay? So which implies that say the average of the infection time is larger, at least larger than exponential with a plus. And actually you can really push this argument to a point where you really compute exactly the constant, okay? Okay, so given this example, so we propose a refined classification of supercritical system. So we say that a supercritical system is rooted if there exists two non-opposite stable direction. Otherwise, it is unrooted. Okay. So, for example, the yeast process is rooted because we have, well, actually many non-opposite stable direction. And so an unrooted model, for example, is you need an infected vertices either to the left or to the right of you horizontally. Okay, so these have as just two opposite stable direction. So the main difference between rooted and unrooted is the following: that in rooted system, so I just draw the picture for the yeast model just as reference. Okay, if you have an initial droplet of infected vertices, which is this yellow guy here, then this droplet can only move in this sector or cone, okay, delimited by the black line, okay, cannot go backwards, okay. Instead, in unrooted system, well, actually it follows from the work on Bootstrap or percolation that a large enough droplet can actually move back and forth, okay, along at least one direction, okay. So this is the main difference between the two situations, and so the conjecture, which is okay, we are rather confident that now we are able to prove the conjecture, is that there is the following difference between the scaling of the infection time. Okay, so it's still random, so we mean this either in mean or with high probability, that if the system is unrooted is 1 over polynomial, and otherwise behaves like the yeast model, namely p to the some constant log 1 over p, divergent if the system is rooted. So in particular, in the unrooted case, it seems that the infection time should scale like the scaling of the critical length of the corresponding bootstrap percolation, while in the rooted case it is much larger, okay, because it's like that, okay. So behind the conjecture, maybe so quick discussion of the unrooted case. So okay, so here there is a direction in which a droplet can go back and forth, and therefore we can compare the KCM. We can do a renormalization, so consider a renormalized one neighbor model in which each vertex actually represents a droplet, and we say that the droplet can be infected if the left or right droplet is completely infected. For this last model, we know the infection time or the relaxation time actually, and we can compute like an effective value of p for the renormalized model, and by comparison the two Markov chain, where comparison means the standard the canonical way to compare reversible chain with the same reversible measure, so by comparing the Dirichlet form, then we get that the relaxation time of the original model is also polynomial in 1 over p. And instead, for the rooted case, so the plan is to mimic the Chung-Daconis-Graham combinatorial algorithm to prove that in order to infect some faraway region, we need to produce logarithmically many new infected vertices, and then mimic the proof for the south or west model. Okay, so this is we are pretty confident that both situations are under control. Okay, so far I discussed the supercritical case and introduced this classification. Now, what about critical system? Okay, so critical system. Okay, we have to do a little distinction between system. So critical system that is rooted, actually alpha rooted, or alpha unrooted. So maybe I'll skip a little bit this also because there is little time. So, but we put forward the following conjecture that if U is alpha unrooted critical, for example, the classical bootstrap process, the two neighbor process, then really the infection time scales like the critical the critical length for the corresponding bootstrap process. While for alpha rooted, this famous Duarte model, it should scale it should diverge much faster. Okay, but this is still in perspective. Okay, and okay, so I have 5 minutes. Maybe I'll try to just describe a possible strategy. Okay. So I'll describe something for the two neighbor model. So this is the classical bootstrap model in 2 dimensions. So I declare that a box is good if any column has at least one infected vertex. And if you take the side of the box 1 over p times some polylog, the probability to be good is very, very high. Okay? And then I say that a box is super good if it is good, and also so there exists one column and one row that is completely infected. This now is very unlikely. Okay, is an unlikely event. However, so if I have a super good box like this one, so green means infected, okay, and next to it there is a good box, then it can be shown that you can swap the two boxes, okay, like that, by creating at most, say, proportional 12 new infected vertices. So the cost is 1 over p proportional 12. Okay, so that's relatively easy. And then what we can prove is the following. So remember that in order to control the infection time, we need to control the relaxation time, and therefore we need to prove a constrained Poincare inequality. So the Poincare inequality that we begin to prove is the following. So imagine that you partition you cover your lattice with boxes of side 1 over p times some polylog in 1 over p. Okay, then and then you introduce this new constraint for the box at x. Okay, that there are two paths of good boxes like this one and this one of length, which is essentially what you want, exponential 1 over p times polylog of 1 over p. And these two paths are all good, so green, and they end with a super good box. Okay? So actually we show that we prove that this Poincare inequality, constrained Poincare inequality holds, and the cost in having that, so the cost between variance and this fixtures or auxiliary Dirichlet form is exponentially 1 over p, and this tilde means that I'm not writing polylog correction. Okay, so once we have this path ending with a good box, then we can start to use this swapping argument. Namely, we try to bring this box, this super good box, super good means a column and a row that are completely infected, along the path. Okay, and we can do that by only pay an exponential in 1 over p cost. Okay, and we do that until we bring the two good boxes right around the box where we are computing this local variance. Okay, So the main tool for that is, canonical path for reversible Markov chain, which is like a standard techniques nowadays. So the conclusion is the following. So now we have to, so this is an enlargement of this box where we want to compute this local variance. So we want to compute the variance here, okay? And actually, we want to compute this variance in terms of variance on individual vertices, okay? So we want to do a flip here. And we know that we have these super good boxes north and east, so with all these infected vertices. But then there is no problem. We can start to slide, for example, this row down. For example, this guy here can become green, and then green, green, green. So we can slide down this row down to here. We can slide this column to the left up to here. And finally, now we have that this vertex has a green, has two green neighbors, and we can do the flip. Okay? So if you put everything together, the total cost for doing that is exponential 1 over p, apart from polylog, and therefore we succeeded in improving a correct Poincare inequality with a weight, which is this is basically apart the polylog, the critical scale. Okay, so the goal, of course, is to do this for any critical alpha-rooted system, but the method seems to be quite robust. So summary is the following: is that characteristic time scale for KCM may scale very differently from the corresponding length scale for the Bootstrap model. And the new feature of KCM, that's something that Bootstrap process cannot detect, is the possible presence of energy barriers. Namely, in order to infect something far away, you need to infect a lot of people that help you to infect your final target. And the presence of these energy barriers call for a more refined classification, which seems to be able to distinguish between systems in which energy barriers matters or not. And it seems that a universality result emerges exactly as for Bootstrap process. Okay, maybe just a last slide. Okay, yeah. So far we just discussed the infection time. Okay. However, for this KCM, there are also other interesting questions. For example, start with a single vertex at the origin. How long does it take to infect a faraway X? Is that linear? For example, for this model, we prove yes, this is linear. So is the speed or the time to infect a vertex depends on the direction of the first vertex with respect to the origin? Again, yes. Okay, very much. This is like is a little bit like first pass at percolation problem. And so even more, so start with a single vertex at the origin and wait until time t and color all the vertices that have been infected by time t, at least once. Okay? Then you get exactly this picture. Okay? And so problem 1, is there a shape theorem? Namely, if you renormalize this set by t and send t to infinity, does this converge to some convex set? And what are the fluctuation of the boundary for large t? So this problem actually was solved in 1 dimension. The shape theorem was proved by Jurgen Blondel, and with Ganguly and Eyal Lubitsky, we proved Gaussian fluctuation of the front in 1 dimension, but in 2 dimensions, this seems to be a big and very interesting problem. Thank you.
Quick questions or comments?
You mentioned that if you have containment of the stable sets, it doesn't imply...
Sorry?
You mentioned that if you have containment of the stable sets, it doesn't imply that the relaxation times go the way around. But
yeah.
Is that strict containment? Do you have nice examples for that? Or?
Yeah, we have we discussed with Christina some example which right now I don't remember, but I remember doing the computation, and yeah,
Maybe I'll ask you later.
yeah, it's false. Yeah.
You ended with a difficult question. A difficult question the other way is, this is all in 2 dimensions. Can you do anything similar in 3 dimensions?
Let's say, yeah. So this actually, for example, the fact that the time is linear, we know in any dimension. Yeah, and the fact that the velocity depends on the direction of this, we did only in 2 dimensions. Yeah, this shape theorem seems really a big step forward, I would say. Yeah.
Maybe any more questions over coffee? So just thank both of you.